Hello all, welcome back to Methods of Operations research course. We were talking about the solution algorithms for integer programming formulations, and we started learning about the branch and bound algorithm. In our previous lectures we solved an example problem, and also we learned the general steps of the branch and bound algorithm. And in today's lecture we will solve another example problem. So let's get started. So assume that we are given this integer linear programming formulation, and we want to find the optimum solution to this maximization problem where x1 and x2 are integer variables. Okay, so how do we solve it using the branch and bound algorithm? If you recall the steps of the branch and bound algorithm, the first thing is to relax this problem, and the relaxation that we are using is the LP relaxation, which means that we ignore this integrality constraint, and the remaining part of the problem becomes a linear program. And in order to solve it, we can use the simplex algorithm, but of course, since this is a smaller example, it includes only two decision variables, we can use the graphical solution method. And depending on the solution that we obtain for this relaxed problem, we will get some information about the integer problem, integer programming solution. And we try to fathom, the first thing is to try to fathom the branch. And basically there were three reasons for fathoming a branch. Whether the LP problem that you solve is infeasible, you cannot obtain any solution for that, and then you fathom, or you obtain a feasible solution and you obtain an integer solution, all decision variables are integers, then you fathom, or the solution that you obtain from this LP relaxation is worse than what you already know, what you already have for the integer programming formulation. That's another reason for fathoming. So the first, when in the branch and bound algorithm, when we solve a problem in one of the branches, the first thing is to try to fathom that branch because of these reasons. If you cannot fathom because of these reasons, you branch it. Okay? And you continue with the algorithm by considering each of the open nodes one by one until there are no remaining open nodes. So let's solve this example problem using this algorithm, and we will solve the LP relaxation using the graphical solution method. Okay, so this is the feasible region of the problem, the x1 and x2 axis. And if you sketch the two constraints, you can find the feasible region of the LP problem as this shaded region. And the objective is to maximize the problem, and when you move in the maximizing direction, we find that the optimum solution to this LP relaxation is this corner point. And that corner point actually is x1 equal to 4.6 and x2 equal to 4.15. So this is the first first solution that we obtain in the branch and bound tree. Okay, so when we solve a problem using the branch and bound algorithm, we record our solutions in a tree-like structure, starting from, as I told you in our previous lecture, in some books you will see that they start counting from 1, but in some of books they start from 0. I will start by counting from node 0. Okay, this root node will be named as node 0. Okay, root node actually is the LP relaxation of the problem where both x1 and x2 are greater than or equal to 0. Okay, this is the relaxed problem. And when I solve it, let me write the solution here. Okay, so this is the first LP problem that we solve, and we obtain x1 equal to 4.5, x2 4.6, sorry, and x2 equal to 4.15, and the z value for this one is 8.75. Okay, so in branch and bound algorithm, in the first step, we, if you remember, we said that we need to always keep track of the best integer solution that we know until that time. And initially, when you start this algorithm, since there is no integer solution that we know, we set the z value to be minus infinity. For a maximization problem, we set it to minus infinity. And when we obtain some integer solutions during the algorithm, we update this best solution. Okay, we will always keep track of this best solution. And currently, we don't have any, so it is minus infinity. So when we solve this first LP relaxation, now we need to check, can we fathom this node? And can we fathom it because of infeasibility? No, because this LP relaxation has a feasible solution. We already found it, so we cannot fathom because of infeasibility. Can we fathom because of optimality or because of integrality? No, because the decision variables x1 and x2 must be integers, but they are not. So we cannot fathom because of integrality. Can we fathom it because of bound? So this question is critical because it is for a new learner, it's a little bit difficult to figure out. What you need to compare is, you need to compare the best integer solution in your hand with the z value of this current solution. Okay, the z value of the current solution is 8.75. And the best integer solution that we know until now is minus infinity. So for a maximization problem, which one is better, minus infinity or 8.75? Of course, 8.75 is better. So it means that the solution in my hand is worse than this one. So there is this branch, when we solve it, when we continue solving this node, we may obtain a better solution. There is such a possibility. Of course, at the end, maybe we will not be able to find it. But the thing is, currently we don't know if there is or not. But the thing is, there is such a possibility. Therefore, we cannot fathom because of bound. It means that I need to branch. And again, last time we discussed, we need to branch on a decision variable. Sometimes new learning students do this mistake and say that, okay, for example, x1 and x2 both are not integer, so they say that, okay, x1 less than or equal to, I'm going to write 4 here, and then go and write x2 less than or equal to 4 to the other side. They are using different variables on different sides of the branch, and this is totally wrong. Okay, we will select one of the decision variables and we will branch on that decision variable. That's very important. Okay, don't do this mistake. And which variable shall we select, x1 and x2? You can select any one of them. Okay, there is no rule. Sometimes in the question it is said that a branch on a variable which is closer to an integer value. If there is such a statement, you need to check the variable values 4.6, 4.15. Which one of them is closer to an integer? So 4.6, the closest integer is 5 and the difference is 0.4. 4.15, the closest integer is 4 and the difference is 0.15. Look, the closest integer can be a lower one or a higher one. We are looking at the closest integer and we are looking at the difference, and if the difference is lower, then we select that variable to branch on. Okay, but this is only when it is stated. If otherwise, if there is no such statement, you can select any one of these decision variables. And for this example, I am going to select x1 as the variable to branch on. Okay, then when we select x1, what are the two values. What are the two constraints that we are going to implement? Since this value over here is 4.6, I need to select the smaller and larger integer values, and I should say that it is less than or equal to smaller integer, it is greater than or equal to the larger integer than 4.6. So I have two branches now, and there are two nodes, two open nodes we call them, and algorithm proceeds by selecting one of these. So which one shall we select? Again, there is no strict rule. If nothing is stated in the question, you can select any one of them. And I'm going to select this one, and when you select it, you number the node. Okay, until you make the selection, we do not number the nodes. The open nodes remain unnumbered. Okay, so now this is the second LP. What is this second LP? It is the original LP, this gray shaded region, plus this constraint x1 less than or equal to 4 implemented. So what is that constraint? Look, x1 less than or equal to 4 is this constraint. Okay, now as you can see, this part over here now removed from the feasible region, and the new feasible region is this shaded area now. Okay, is this enclosed, green enclosed area. Now we are going to find the best solution in this region, and when we do it in increasing direction, we can find that this is the new optimal solution to this problem. What is that problem? It is LP. I'm going to sketch it here. Okay, so if we call this as LP0 or LP1, again, it's not important which one you select from starting. This is LP1. So in this LP1, we implement this constraint, and when you solve it, we obtain this solution. x1 is equal to 4 and x2 equals to 4.4, and the z value is equal to 8.4. Okay, so this is the solution in this corner. Now, when you solve this problem, again, the first thing is try to fathom this node. Can I fathom it because of infeasibility? No, because there is a feasible solution. Can I fathom it because of integrality? No, because x2 is 4.4, it is not integer. Can I fathom it because of bound? Now, what is the best integer solution that we know until now? It is minus infinity. And what is the z value here? 8.4. 8.4 is better than minus infinity for a maximization problem. So we cannot fathom because of bound. It means that I need to branch. Okay. So as soon as we do this decision, we make this decision to branch, we open two branches. Okay. And branch on which variable? x1 is already integer. We never branch on an integer valued variable. So we need to select a variable which is not integer. In this case, it is x2. Okay. And what should I do? Again, I should select the smaller and larger integers than 4.4. And I should write x2 less than or equal to 4 and x2 greater than or equal to 5 to these left and right hand side branches. Now I have three open nodes, as you can see, three open nodes, and I have to select one of them as the next one. So which should I select? Again, there is no strict rule, there are no conditions on it, but basically there are some guidelines. The first guideline says that depth first search. In depth first search, when there are multiple open nodes, you select the one which is in the deepest level. Okay, so I told you that these branches are written as levels. So this branch is in level 0, then these two are in level 1, and these two are in level 2, and it goes like this. And according to depth first search, when there are open nodes, you select the open node which is in the deepest level. Of course, if there are two nodes in deepest level, which one you should select? Again, you can select any one of them. That depth first search does not say anything. But when you compare these two with this one, according to depth first search, you have to select one of these two. Another approach is the breadth first search. In breadth first search, you select the open node which is at a higher level. Okay, higher level means this one. Okay, so according to breadth first search, we have to select this one first, then the others. Okay, in this example, I am going to implement the breadth first search approach. Okay, so I will select this one, this breadth first search. According to breadth first search, I have to select this one. And what happens? Okay, so what is the problem that we are solving on this side? Remember, on this side we implement this constraint. Do we have x1 less than or equal to 4 on this side? No. So it means that we have this feasible region in LP2. We have this feasible region plus this additional constraint which says that x1 is greater than or equal to 5. So it should be go from here. This is 5. And it is greater than or equal to 5. And as you can see, this feasible region and this constraint does not intersect. What does it mean? What is the optimum solution for at this branch? There is no solution. It is infeasible. The LP problem is infeasible. So what can I say here? I am going to fathom by infeasibility. Okay, so this branch is closed now. It is fathomed due to infeasibility. Now there are two open branches. I need to select one of these branches. Which one should I select? Again, you can select arbitrarily any one of them. I am going to select this one. So since we selected here, I need to number it as 2. And then I am going to select this one over here, and it will be number 3. And look, in this one, which constraints do I have? Which additional constraints? First of all, this one is already implemented on this branch. I already have it. Okay. Plus, I have x2 less than or equal to 4, which means that I also have this constraint. And the new feasible region that I am considering is this green part now, the yellow shaded region now. And when we solve this one, okay, what do we have? This is our LP3, and when we solve it, we see that x1 is equal to 4, x2 is equal to 4, and the z value is equal to 8. Okay, can I fathom this? Due to one of these three reasons. And when you check the values of x1 and x2, we see that both of them are integers. So it means that I can fathom because of integrality. All decision variables are integers. Okay. And when we fathom by integrality, or sometimes we call it optimality, when we fathom because of this reason, okay, we need to check what was the previous integer solution that we know. It was minus infinity, which means that we haven't got any integer solution yet. We don't know any. And now in this one, we have an integer solution, and the objective function value of this integer solution is 8, which is better than minus infinity. So it means that I am going to update this value. Okay. So let me put a star here to differentiate it from the current solution. This best integer solution now is my infinity. Okay, this is a critical node, critical point. Okay, we are not saying that this solution is optimal, but it is the best solution that we find until now. In the remaining part of the algorithm, maybe we will find a better solution, but maybe not. Okay, if we cannot find a better solution, then this will be our optimal solution. Otherwise, we will find a better solution, and that one will be the best solution. Okay, so now I have only one node remaining, which is this node. I number it as node number 4. And in that node number, I'm implementing x2 greater than or equal to 5. So which region? Again, you should be careful. In this part, I don't have x2 less than or equal to 4. I have x2 greater than or equal to 5, which means that I have this constraint. And the intersection of all these constraints is this region now. Okay? On this LP4 over here, I am solving the problem for this corner. And when you solve it, we obtain that x1 is equal to 2.5, I guess. x2 is equal to 5 and z value equal to 7.5. Okay. Now when we solve it, again, the first thing is to try to fathom this. Can I fathom it because of infeasibility? No, because there is a feasible solution. Can I fathom it because of integrality? No, because x1 value is 2.5 and it is not integer. Can I fathom this because of bound? Now, this critical question, can I fathom it because of bound? For this, I need to compare the best integer objective value, which is 8, with the current objective value, which is 7.5. So for a maximization problem, look, it is very important. This is a maximization problem. And for a maximization problem, 8 is better than 7.5. So the previous integer solution that we obtain is better than this relaxed solution. So it means that you don't need to consider the rest, because this is the best. This 7.5 is the best that you can get from here. Although it is not integer, it is the best. If you find an integer solution in this triangle, in this region, it will be either the same 7.5 or it will be worse than 7.5. This 7.5 is the best, and our previous integer solution is better than this one. So why you are trying to find that solution in this region? So we can fathom this by bound. And if you look at the branch and bound tree, there are no other solutions, no other open nodes. It means that we stop. The branch and bound algorithm stops. Okay, we stop the algorithm, but what is the optimal solution? In order to identify the optimal solution, you need to, as I told you, keep track of this best integer solution in all branches, and the best integer solution is 8 when we stop. And where did we find this best integer solution? We updated it in this node 3. So it means that this solution over here is the best integer solution. Meaning that, let me write it here, x1 star is 4, x2 star is 4, and the z value equals to 8 is the optimum solution that we obtain from this branch and bound tree. Okay, so this is how we implement the branch and bound tree to solve this simple problem. As I told you, depending on which variable to branch on, for example, here we selected x1. Instead of x1, if you selected x2, you would find the same optimal solution. The optimum objective function value will be 8. But maybe you will find it in a more longer, a branch and bound tree. The procedure may be longer. We may not know it. Again, when there are, for example, multiple nodes are opened, depending on which one you select first, the procedure can be shorter or longer, and we may not know them. And by this example, we learned these two procedures, depth first search and breadth first search. So in our following examples, if we say implement breadth first search, you should be able to knowing which node to select next, or when we say depth first search, you need to know which node to select as the next one. So we will continue discussing the branch and bound algorithm in our following lectures.